everyone, in this video you will learn how to efficiently determine the longest palindromic substring. Palindrome is a sequence that reads the same backwards as forwards. The longest palindromic substring can be found in a variety of methods. Naive approach for finding the longest palindromic substring is by checking each substring if it is a palindrome or not and by keep updating the longest palindromic substring found till then. Three nested loops are needed to find the longest palindromic substring in this approach. So, time complexity is order of n cube. And there is also another approach using dynamic programming which takes order of n square. These two methods were incredibly difficult for the computer to process. They had high time complexities and well, they are difficult too. This is because complexity of algorithms are high. So we have to find another method which is going to be discussed in this video. This algorithm find the longest palindromic substring in order of n complexity. That is Manacher's algorithm. Now let me discuss the Manacher's algorithm. The first step in the Manacher's algorithm is to create a new string by inserting a special character between each pair of characters in the original string. It ensures that every palindrome in a new string has an odd length. Initialize two variables, center and right. Center of the palindrome we have found so far and the right represents the rightmost boundary of this palindrome. Initialize an array P to store the length of the palindrome centered at each position in the new string. Initially set all the elements to the 0. And the fourth step in this algorithm is the main step. So let me be more clear about it. In this step, we are focused on expanding palindromes centered at each position in the new string. First step in this is looping through each position I in the new string. This loop goes through each character position in the modified string where we have inserted a special character between each pair of characters in the original string. Updating the palindrome length pi at the position I. If the current position I is less than the right boundary of the current palindrome, we update p of I using previously discovered palindrome information and avoid redundant work. The formula used to update pi is equals to minimum of p of 2 into center minus I and right minus I. You may all be wondered like why is that 2 into center minus I? Let me explain. 2 into center minus I represents the mirror position of I relative to the current center of the palindrome. Right minus I represents how far I is from the right boundary of the current palindrome. Taking the minimum of these two values ensures that we update P of I appropriately based on the known palindrome lengths. And the third step in this is expanding the palindrome centered at I. After updating P of I, we expand the palindrome centered at I as far as possible. This expansion involves checking if the characters on the both sides of I in the original string are equal and incrementing the palindrome length P of I accordingly. And the final step in the fourth step is that updating the center and right boundaries. If the right boundary of the palindrome centered at the I extends beyond the current right boundary, we update the center and right accordingly. This ensures that we keep track of the longest palindrome found so far and its boundary. The final purpose of this step 4 is to efficiently update and expand palindromes centered at each position. This step plays a crucial role in achieving linear time complexity for finding the longest palindromic substring in the given string. And next, find the index of the maximum value in P. It represents the center of the longest palindrome in this new string. And the final step is that use the center and palindrome length to extract the corresponding substring from the original string. Now let me explain with an example which will help you to understand more better. Let me explain Manacher's algorithm with an example. Let the string given be A, B, A, B, C. The first step of the Manker's algorithm is to create a new string by inserting a special character between each pair of the characters in the original string. Let that special character be hash. Now we'll insert the special character between the each pair of characters in the original string. And the resultant new string will be hash A, hash A, hash A, hash A, hash A. This will be our new string of length 2 into n plus 1. And now next step is to initialize an array to store the length of the palindrome centered at each position. Now we have to initialize an array with the length 2 into n plus 1. After initializing an array with the length of this new string, we need to calculate the length of the longest palindromic string at each of these positions. At the position 0, there is no longest palindromic substring at all. No characters on the left side of this hash to compare. So the value at this position will be 0. And at the position 1, longest palindromic substring will be hash A hash. The number of strings before this A will be 1 and the after this A will be 1. These three combined together form a palindrome. So the value corresponding at this position will be 1. And at the position 2, there is no longer palindromic substring at all. Left character of this hash is A and the right character of hash is B. They do not match, they don't even form a palindrome. So the value at this position will be 0. And at the position 3, which is now we have to calculate the value of this 3. See, now the value to the left of this B is hash and to the right of this B is hash. They both match. So these three form a palindrome. And also value to the this side is A and value this side is also A. These five together form a palindrome and value of this is hash and this is also a hash. So these seven form a palindrome. The number of strings before this B is hash A hash is 3. So the value corresponding to this B is 3. Unlike the position 4, there is no longer palindromic substring at all because the character to the left of this hash is B and the character to the right of this is A. They don't match. So the value of this is B. So enough like this we need to fill total array. And yes, we are done by calculating length of the longest palindromic string at each of these positions. Do you think that this takes order of n? No, obviously. This takes order of n square. And now we have to calculate this longest palindromic string length array efficiently. If we have a look at this array, we'll observe something. If we look at more closely, we'll find a mirror property here. Like the numbers before this 3 is 1 and 0 and the numbers after this 3 are 0 and 1. Don't you think that 3 is a mirror and these two and these 5 are following a mirror property? Exactly. Now, based on this mirror property, we will to calculate the longest palindromic substring length array efficiently, we need an array, a pointer which iterates all over the string, and also a dashed mirror line. As you see, as you see, the dashed line is the line along which the current mirroring process is going to exist. We are going to check the mirroring process by using the mirroring line predict. Interesting, right? Of course, all the values are set to 0. Initially, so let's begin our quest to find the longest palindromic substring. The first letter doesn't really have a lot of prospects. Here, its value is bound to be 0 because there is no character to the left side of this first value. So the value will obviously be 0. And now our iterator will jump to the next pointer. Charac- on the next character, we encounter a A. Now the pointer is pointing towards A. Now expanding on the left and right sides gives us the value 1 because there is a hash on the left side and there is a hash on the right side. which these three combinedly together form a palindrome. As there are value, as there is a one string on the left side and the one string on the right side, the value corresponding to this position will be 1. As we encountered a palindrome, we will set a new variables L and R to track our palindrome. These L and R are known as left and right markers, indicates where the palindrome begins and where it ends, corresponding to the current mirror center. Now we move to the next character. As we move to the next character, we see that our right pointer and our left and our current pointer and our right pointer are on the same letter. So now, this mirror property doesn't work well on the start and end characters of the palindrome. It's just, it just doesn't usually because being at the edges at the end and starting there, mirror counterparts are always mostly values of 0, which anyway is the default starting value. There is no use in wasting processing power over them. We directly move to expanding them on the right and left, ignoring their mirror. In this case, you can't even expand it as it has A on the left side and B on the right side, which don't even match. So there is no value, so there is no case of updating it. This will be 0 as usual. And now our pointer moves to the B. Now our pointer is on B. We see that B is outside of our scope. As it is outside of our scope, you can't really do much with the property of mirroring. So we proceed to expand it and get the palindrome. And now if we expand it, we'll get a palindrome A hash B hash A. This is a palindrome. And even if we expand more, we'll even find a palindrome from starting with here. Hash A hash B hash A hash of length 3. So we'll update the value of here, value of 0 to 3 here. Expanding is actually trying to find the palindrome with center at B. So here center will be basically collecting 3 characters in the left and the 3 characters in the right. So the value of this point will be 3. So as we have encountered our new palindrome, we'll update the values of left and right. This will be here, because the leftmost part of our palindrome is this and the rightmost part of our palindrome is this. And now next our pointer will be updated. The mirroring property will be applied on this hash value. When you think about it, value here has maximum potential to be index of r minus index of r minus index of the current pointer. This will give us a value of 2 because we are mirroring from 3. 3 right, the character has a value of 3 at now our pointer is shifted to the next one. This will be having a maximum potential to have the value at the point index of right pointer minus index of the current pointer, which is the 2. But the value which we'll choose is the minimum between the mirror value, which is on the left hand side, and the index of a r minus index of the pointer, which is generally 0 versus 2. As we know, minimum of 0 was 0 and 2 is 0, so the value of this point will be 0. And next it will be updated to A. Now our pointer is updated to A. We know that in before case we have discussed that this can take the maximum value of r minus current pointer, and now this can take the value of r minus current pointer, which gives 1. And also we know that we will take the minimum of this mirror property and the r minus current pointer, which is 1, and and here also our right pointer and the current pointer subtraction gives us 1, so we can update it to 1. And now our pointer is moved to here. we can see that our current pointer and right pointer are on the same side. We know that mirroring property doesn't work well on the extreme edges. So now we'll try to expand this. And by expanding this, we'll try to find a palindrome. Here it is A, so this will form a palindrome. Here it is hash, here it is also hash, it may form a palindrome. Here it is B, here it is B, it may even form a palindrome. Here it is hash, here it is hash, it also forms a palindrome. And here it is A, and here it is C, it doesn't form a palindrome. So we found that the palindrome will be of length 9. We have four characters to the left of this hash and four characters to the left of this hash. So the value at this will be 4. As we have encountered a palindrome, our left and our pointers will be updated. Our pointer will be here and left pointer will be here. It is not clearly shown, but still. The left pointer will be here and the right pointer will be here. And the current pointer will be shifted to A. According to the mirroring property, it will hold the value of 1, minimum of 1, comma, and this will this will hold the property of right pointer minus current pointer, which gives us 3. Minimum of 1 and 3 is 1, and so the value will be stored here is 1, and now the pointer is updated. Similarly, we'll fill this. Our LPS array is filled. And now we'll find a maximum number from this array, which is 4. So it is easy to find a maximum, so it is easy to find the longest palindromic substring, which is hash B, hash A, hash A, hash B. This is the longest palindromic substring, which gives B, A, A, B. This will be the maximum. This will be the longest palindromic substring of the given string A, B, A, A. Now let's have a glance on code implementation. Inside find longest palindromic string function, the length of the input string is calculated and stored in n. If n is 0, the function returns early. N is updated to represent the length of the modified string. The modified string contains special characters at the beginning and end respectively and duplicates every character of the input. Initializing variables. An array L of size n is created to store the length of the longest palindromic substring created at each position. Variables C, R, I mirror, expand, diff, max LPS length, max LPS center position, start and end are initialized for tracking the algorithm's progress. Main loop. The loop iterates from index 2 to n-1 inclusively. For each position I, it calculates the mirror position I mirror with respect to the center C. It handles 4 cases based on the distance between I and the right boundary R. Case 1. In case 1, no expansion is needed. And case 2, expansion required if R is at the end of the modified string. Case 3, expansion required if R is not at end of the modified string. And final case is that expansion required due to significant difference between L of I mirror and diff. After determining if expansion is needed, it performs palindrome expansion. For odd positions, it compares characters and increments L of I by 1. If they match and for even positions, it increments L of I without character comparison. The algorithm tracks the maximum length of the palindrome which stores in max LPS length and its center position max LPS center position. It adjusts the center C and right boundary R if expanded palindrome exceeds R. Extracting the longest palindromic substring. Once the algorithm completes, it calculates the start and end position of the longest palindromic substring based on max LPS length and max LPS center position. Output. Finally, it prints the longest palindromic substring found in the input string text. And now In main function, input is taken from the input file. That input file consists several inputs. There is also a best case input and also a worst case input. Best case input is that the given string is itself a longest palindromic substring, and the worst case is that there is no palindrome found in the total string. Here are the outputs of the input file.